மற்ற கிளாஸ் எழுதுன்னு எல்லாம் மறந்துருந்தீங்கண்டியா? அது கரெக்ட் ஆச்சா? வாவர்ல வந்துதான்.
ஓகே.
Sir, please unmute yourself. Lokesh sir.
Hello.
Yeah, sir.
Hello.
Hello, okay, sir.
Okay. Yeah. So, so today we will go for the day 3. Here, so in the previous class, what we have seen is we have seen about the IoT, Internet of Things. So we have seen about the definition and architecture, how it is going to be working, and what are the applications. So definition is nothing but, so IoT is nothing but a embedded system which can be capable of connecting to the internet and sending the data. So if I see the architecture, I'm having a sensor which can be capable of sending the data through the internet. So from there, we are going to be having a cloud. In the cloud, we will analyze the data and we will send the user requirement notification. So that's how we are going to be having. And we have seen about some of the applications of the IoT. So majorly, I will go for the traffic management. IoT, one of the case. So traffic management is nothing but in a smart cities, we need to manage the traffic. So for example, especially if I am having a ambulance situation, so we need to handle this ambulance situation very carefully. So in those situations, what we are going to be having is, so we are having a sensors, are all the sensors are going to be connected. So these sensors, all the sensors are going to be connected, and these sensors are going to be giving the data continuously. So from this sensor, we can able to say that, so how the traffic patterns are there, and all those things we can able to find out, and we can able to give the better solution for the traffic management, like that we are having. So today what we will go is, we will go for some more details about the embedded system. So if you see the embedded system, what are the elements we are going to be having in the embedded system is, so these are the elements. So I can able to, so I think you can able to see my screen. So there we are having a elements like, so first we are going to be having a system core. The system core is nothing but where we are going to be having our processor. So there is a system core. Yes. Oh, sorry. Yes. 1 second, please. Yes. Yes. Here you can able to see the system core. So system core is nothing but microprocessor, and you can able to see the input ports. The input port is nothing but sensor. Next, you can see the memory. So the one of the memory. Next, you can see the where in the memory we are going to be putting the embedded firmware, and we can able to have the one more block which is going to be as like a communication interface block, and we can able to have the output block. So like this, a typical real world embedded system is having a these type of 6 blocks we can able to say as it. The heart of the embedded system is a processor, which can be called as a system core, and we are having an input block. We can input block, in the input block we can able to say that the sensors, so sensors are going to be connected in the input block. So for example, in the picture you have given a switch. Switch is the input. Next, we can able to have the output block. So in the picture you are going to be seeing the buzzer is the input output block. Next, we are going to be having a memory. So the memory is nothing but embedded firmware. So where we are going to be writing the program. Okay, all the program is going to be loaded into the memory of the embedded system, and we are going to be having a communication interface block. So from the microprocessor, if I need to communicate to the outside world, so we need to have the communication block. For example, I need to have the Wi-Fi connection. So Wi-Fi connection is nothing but communicating with the outside block. So there we can able to have this one. So what we will do is, so we will quickly go through all these sections, and we will come to know the important basics in the embedded system. So this class is very important. So because you know the things already, but these things are somewhat confusing. So that's why what I will do is quickly I will go through all these things so that you can able to know the each and everything clearly. Then we will go for the programming. So then you can able to easily understand the programming and all those things. So that's why please listen this session very carefully. Next. So if I go for the next thing, so the core of the embedded system is going to be having a first thing is going to be called as a core. So core is nothing but what I have told you is core is nothing but the microcontroller or microprocessor. So there we are going to be having a different types of processors or different types of microcontrollers we are going to be having. So if you see the classification, where we are going to be having a general purpose and domain specific processor. So there we can able to have the microprocessor, microcontroller, digital signal processor. Next, if I go for the one more thing, which is going to be called as a application specific integrated circuit, which is going to be called as a ASICs. Next, we are going to be having a programmable logic devices, and fourth one we are going to be having a commercial off the shelf components. Like this, we are going to be having a different component, different classifications for where we can able to utilize all these core embedded system. So before going to this one, so first what we need to know is we need to know about the what is meant by microprocessor and what is meant by microcontroller and what is meant by digital signal processing. So processor, we know the things very clearly, but I will go through that one. So for example, let us take So to understand this one clearly, so first what we need to know is, we need to know one thing which is going to be called as a microprocessor. Previously, what is meant by microprocessor is nothing but, previously we are going to be having a CPU. The CPU is nothing but, it's going to be having a four different components like control unit, registers, ALU, bus interfacing unit. Okay, so what people done is, so they try to implement all these things into a single chip. CPU is going to be having it a single chip. So that is going to be called as a IC, which is going to be released in the 1971 by the Intel, is going to be called as a 4004. So that is going to be called as a microprocessor. So previously, the system or computer is going to be having a very heavy, it's occupying a very heavy spaces. Like it's going to be having a one or two or three floor buildings, it's going to be occupying like that. But whenever the Intel started to create a microprocessor, so what it done is, it convert the CPU, the 4 blocks, into a single chip, So that's going to be called as a microprocessor. Next, we know about the microcomputer. Now we need to know about the microcomputer. So microcomputer is nothing but microprocessor plus memory plus IO on a single PCB. So if I take a PCB upon that one, so what I will put is, I will put this IC, microprocessor IC, and I will put the IO devices and memory. Okay, then that's going to be called as a microcomputer. So that's the second version. So previously the computer is going to be a very large, now it became as a very micro size. Next, the third thing is microcontroller. So microcontroller is nothing but microcomputer on a single chip. So I will put all this computer into a single chip. That is nothing but, I'm having a CPU, I mean to say as a microprocessor plus memory plus IO devices in a single chip. So that's going to be called as a microcontroller. So the first microcontroller which are going to be released is by a TMS. So this is a TMS 1000, which is released by the TI company, Texas Instrumentation. So this is a 4-bit microcontroller. So Intel is also having one more microcontroller, which is going to be called as the 8051 microcontroller. This 8051 microcontroller is a very basic microcontroller, so very famous microcontroller. Depending upon this microcontroller, they have generated different microcontrollers. Next, we are having one more thing, which is going to be called as a SoC. So we can able to call it as a system on chip. What is the meaning of the system on chip is microcontroller plus programmable analog. So for example, I'm having a microcontroller. So I need to connect the microcontroller with the, let us take analog devices. So let us take a comparator is going to be connected, or a filter is going to. So I cannot able to control these analog devices, or I cannot able to program these analog devices. So what what they started to think is, why don't we include these analog devices into a single chip, and why don't we program that one? So they started invented, and they invented one thing which is going to be called as the SoC, system on chip. So in the system on chip, so what we are going to be having is, we are going to be having a microprocessor as well as, so we are going to be having a programmable analog things. So that's going to be called as a system on chip. So after that one, we are going to be having one more thing which is going to be called as a COTS. So which is called as a commercial off the shelf components. So what is the meaning of this one? So these, so we need to have only limited analog circuits, or we need to have it specifically. So for particular application, we need to have this type of connections. Let us take I need a USB connector, I need a Wi-Fi connection, I need something like that. So the user will going to be choose. So in the SOC, we are going to be having some fixed one, whereas here we can able to choose. For example, for that one, I can able to say as the example as a Raspberry Pi or Beagle backbone. So these are the examples for the set. So these are the generations. These are the important terminology you need to know. So first one is a microprocessor. Second one is a microcomputer. Third one is a microcontroller. Fourth one is a system on chip. Fifth one is a COTS. So if you know all these things, so then we can able to easily go through now. So first one is a general purpose specific domain. Yes. So you can able to see is now. So here we are having a core of the microprocessor. So we have seen that microprocessor. What is a microprocessor? So they are going to be having a microprocessor is nothing but one chip is going to be connected entirely. So that's going to be called as a microprocessor. So that's the same thing we are going to be having, capable of defining all the circuit and the manufacturer depending upon the manufacturer. So it's capable of performing all the logic and that's going to be called as a micro. So we have seen about this one. So first microprocessor is a 4-bit microprocessor, which is going to be having in the the feature of this one is, so we need to know about some of the features. So what are the features of the first microprocessor? So the microprocessor is going to be having something like this. Is the 4-bit microprocessor. So they are going to be having a 1 kilobyte of the data memory and a 12-bit program counter, and it is going to be having a 4 kilobyte of memory like that. So these are the things we are going to be having. Okay, so like that. So these are things we are going to be having, and it's run at the clock speed of the 740 kilohertz. So like that, we are going to be having the this one. Next, if I go for the next thing, so who are the manufacturers of the microprocessor is, so on those days, so they are going to be having a companies are Intel, AMD, Freescale. So all these things are going to be having a companies which are going to be manufacturing the microprocessors. So you need to know this one also. So these are the things which the microprocessor is going to be manufactured. Next, so there are two different types of processors. You can able to say as a one is going to be called as a general purpose processor, which is called as a GPP, and second one is going to be called as the application specific processor. So application specific instruction set processor. These are the two processors. So depending upon the processor, it's going to be utilized like that. So particularly application specific, or it can be utilized as a general purpose. So like that we are going to do. Next, we have seen about the microcontroller. Microcontroller is something but so microprocessor, microcomputer, and a single chip. So like this is going to be having a RAM, ROM, and IO devices, ports, and all those things. So these are the some of the differences which we are going to be having in the microprocessor and microcontroller. So you can able to see that a silicon chip representing a central processing unit, which is capable of, so that's the thing, and microcontroller is like this. So it's going to be having the IO ports and 8255, all those things. So we have seen this one in the first class itself. So that's why I'm going to give some pass here. So next, so what is the digital signal processor? So what is the difference between the normal processor and digital signal processor? So you know this one better. So in the digital signal processor, the computing is a need very fastly. So we need to find out the FFT or we need to find out the DFT. So for that one, we need to have the number of computations. So that number of computations is going to be increasing. So that's why we need to have the very fast computations. So those going to be called as a digital signal processor. So these digital signal processors are going to be utilized in the signal processing applications. Wherever we are going to be having a signal processing application, so where there we are going to be utilizing these type of applications. So if I'm in the embedded system where we are going to be having a digital signal processing application, so there we are going to be utilizing this DSP. Okay, next. So this DSP is going to be consisting of program memory, data memory, computational engine, IO units, all those going to be presenting in the DSP. So these are going to be having some other computationals like addition, subtraction, multiplication, and division. architectures are different. So we will see that one. So next. So here, yes. So we need to know about the one of the important thing here, which is going to be called as a risk versus risk processor. So we need to know about the first one is what is meant by risk and what is meant by risk. I think you know all these things. So risk is nothing but reduced instruction set. Risk is nothing but complex instruction set computer. So why we are going to be using this one is first we are having an instruction set. So before going to the instruction set, first I need to know need to tell about the instruction. So instruction is nothing but to do something. So we will tell to do something. So before writing the exam, please read these instructions carefully. So instructions is nothing but they will tell how many questions you need to attend, all those things. So that's going to be called as an instruction generally. So like that, if they come for the embedded system or processors, so the instruction is nothing but what the processor need to do. What the processor need to do is nothing but an instruction. So if I combine these instructions, then I can able to write down a program. So if I so the combinations of n number of instructions is something but writing a program. So in the instructions, what we are having is we are having a instruction, or you can able to say as a mnemonic. In assembly level language, we can able to say as a mnemonic. Mnemonic is nothing but English like language. For example, let us take I'm having a MOV A comma B. You know this one. So this called as an instruction. MOV A comma B is nothing but please give me a second. So I will join. 1 second, please. Actually, my laptop is not working properly. That's why I'm taking a 1 or 2 minutes here break. So I will continue. I will resume that after that. Please be patient. So, hello, everybody. Yeah. Sorry for the interruption. So yeah. So now I will try to explain about the what is meant by CISC and what is meant by RISC. So CISC is nothing but complex instruction set, and RISC is nothing but reduced instruction set. Okay. So before going to that one, first we need to know about the instruction. So we have seen about that one. Instruction is nothing but giving a data, giving a yes, giving a command is nothing but instruction. So if combining this sequentially, so then that is going to be called as a program. So we have seen, we have discussed about them. Let us take, I am having an instruction. So that the instruction is going to be move A comma B. So in that one, move is nothing but a mnemonic, and A comma B is going to be called as the operands. Okay. So then, so here, so the number of instructions in a particular system is going to be having a very less number of less number. So that's going to be called as a reduced instruction set. So whereas in the complex instruction set computer, we're going to be having a more number of instructions. So next, if I am having the reduced instruction support, the RISC will support the pipelining. So we will see that what is meant by pipelining, all those things. And whereas CISC doesn't support the pipelining feature. Next, so this is one of the important thing, orthogonal instruction set. So it allows each instruction to operate any register and use any addressing modes. So addressing mode is something, but how we are going to be indicating the operands is going to be called as a addressing mode. So A and B, this A and B are, for example, let us take move A comma B. So these A and B are called as the operands. So whether these operands are the register or directly data, so that what type is going to be told by using this addressing mode. So this addressing modes, so if I am having an orthogonal instruction set, RISC is nothing but orthogonal instruction set is nothing but any type of addressing modes I can able to use, or there is no restrictions. So or any register can be used, whereas in CISC is a non-orthogonal instruction set. So it need to use a particular register. So for example, in 8086, if you remember, in 8086 we are having an accumulator. For every logical arithmetic operations, we must use this accumulator. So then only the results will be stored in the accumulator. So that's one. That's going to be called as a non-orthogonal instruction set. So which they need to having a restriction. So we need to use these type of addressing modes only. We need to use these type of registers only. Like that we are going to be having it in CISC. Next, if I go for the RISC, operations are performed as the register only. The only memory options are load and store. So we will see about what is meant by load and store. So operations are performed on a register or memory depending upon the instruction. So here the operations are going to be only performing on the registers. So it's not going to be performing on the memories. Okay. So whatever the data we are going to be having, we need to take the data into any one of the register and we need to perform the operation. That's kind of like a RISC. So whereas directly the memory locations, we can able to perform the operations. Next, a large number of registers are available in the RISC computer. So for example, if I go for the 8086 processor, they are going to be having a maximum of 16 registers are available. Let us take. So whereas if I go for the MSP 430, we are having a very large number. We can able to say as a 60 to 40 different types of registers are going to be available. So because MSP 430 is one of the RISC type microcontroller. So if I go for the 8051 microcontroller, they are going to be having only 20 registers. Whereas if I go for the MSP 430, it's going to be having about 30 to 40, or you can able to say the 60, approximately 60 registers are going to be having. So like that. So there's a difference between the RISC and CISC. Next, a programmer need to write the more code to execute a task since the instructions are simpler one. So RISC is going to be having a like that. Whereas in the CISC, instructions are like macros in C language. A programmer can achieve the desired functionality with a single instruction, which in turn provide the effective of using the simpler single instruction RISC. Okay, like that. So here the instructions are a single fixed length instruction. So this is CISC is going to be having a variable instruction. So some instructions are going to be having a 1 byte, some instructions are going to be having a 2 byte, like that. So less silicon usage and pin out. So if I go for the RISC reduced instruction computer, so it's going to be utilizing a very less silicon space. So we can able to have the denser in that one. So whereas in the CISC it's going to be utilizing the more silicon space, because we need to have the additional decoder logic circuits, and we need to have the implement the complex instruction decoding, all those things. Next, RISC is going to be having a hardware architecture, whereas the CISC is going to be having a one human architecture. So these are one of the important things. Architecture is one of the important things where so we need to know the architecture inside, how the registers are going to be having. So depending upon that one, we are going to be having a two types of architectures. So we will see that one. One is going to be called as a Harvard architecture, and second one is going to be called as the one human architecture. You know this one. In the Harvard architecture, we are having a single bus. In the one human architecture, we are going to be having a multiple bus. Each and every is going to be having a separated. So like that. So this is the important differences between the CISC and RISC, if you know this one. So now, if I go for this one, what is the one human architecture and what is the one human architecture and what is the Harvard architecture? So this is going to be having a like this. So in the RISC, we are going to be having a Harvard architecture, whereas in the CISC we can able to have the Harvard or one human architecture, whatever the we can able to prefer any one of this one. So that is nothing but, so that's why we need to know about the both of these things. So you can able to see the diagram. So the first diagram is going to be having a single shared bus. So between the CPU, IO and memory. Whereas in the second diagram, you can able to see the CPU is and data memory is going to be having a separate line. So like that, we can able to have like this. So like the differences we are going to be having. So here, first Harvard separate buses for the instruction and data fetching. So data fetching and the instruction and data. I mean to say, as a for instruction fetching and whatever the data we are going to be storing, they are going to be having a separate buses. Okay, so like this. So whereas in the one human, we are going to be having a single shared bus. So both for the instruction and the data. So I need to say as the first diagram, sorry to say that the first diagram is a one human architecture and the second diagram is going to be having a Harvard architecture. So the hardware architecture is easy to pipeline. So that's why we can able to achieve the high performance. High performance can be achieved in the Harvard architecture. Whereas in the low performance compared to the Harvard architecture, in the one human architecture, the performance is very low. Comparatively a high cost. The hardware architecture is a comparatively a high cost. So whereas the one human architecture is going to be having a cheaper. Why? Because in the Harvard architecture, we need to have the buses, separate buses. Whereas in the one human architecture, we are going to be having a single shared bus. No memory alignment problems in the hardware architecture, because each and every is going to be having a different address buses. So different buses. So whereas here we are going to be having allow self-modifying codes. So we can able to have this one here. Since data memory and program memory are stored physically in different locations, no chances for accidental corruption of the program memory. So because it's going to be having a two separate buses and two different memories, that's why so there is no, so there is a problem in that in one human architecture. So that's the thing we are going to be having in the what is meant by the one human architecture and what is meant by the hardware architecture. So if I see this one, so why we need to learn is, so in the RISC computer, we are going to be utilizing the Harvard architecture. So Harvard architecture is nothing but separate buses for instruction and data. separate buses for the instruction and separate bus for the data. So that's why we need to know this one. So most of the modern microcontrollers are using the RISC architecture. That's why we need to know this one. So separate data and separate bus. Next, here we need to know another important basic thing, which is called as a big Indian and little Indian. So Indianness, Indianness, you can say end. So what how you are going to be having? For example, let us take, I'm having a memory. So in that one, so I'm having a data. Let us take, I'm having a, for example, let us take, I need to send the data move a comma 8000, move a comma 8000. Let us take AX, let us take this the instruction which is the 8086 instruction. Example I have taken as the 8086 instruction. I need to move the data. So this is the 16-bit data. 8000 is a 16-bit data. I need to transfer the data to the AX register. AX is nothing but accumulator register. Okay. So for that one, so let us take a memory diagram. So that's why I have tried to connect my laptop, but it's not giving me support. So what I will do is, I will try to switch on my cam. So what I will do is, I will try to explain about you the big Indian and a little Indian. So for explaining about the, you can able to say as a Indianness. So this is called as a Indianness. Okay. So this Indianness is having a two types. One is going to be called as a big Indianness. Second one is going to be called as a little Indianness. Okay, so we need to know about the difference. What is the difference? Yes, I think you can able to see that clearly. So Indianness, big Indianness and little Indianness. Okay.
Sorry, sir, the screen is not visible, sir.
So I started share screen. Okay. All I have to is check my video. So I am sharing my video. I switched on my camera. Is it visible now? Please respond. Anybody, please?
Sir, only MOV is visible, sir. MOV.
MOV. So is it? I have written as a Indianness, two types of Indianness: big Indian and little Indian. MOV. Yeah, let me share my PPT. Good thing. Yes. Now is it visible?
Yes, sir.
Yeah. So yeah. So we will go for the little Indian. Little Indian is nothing but lower order byte of the data is stored in the memory at the lowest address, and the higher order byte store the highest address. For example, let us take move x comma 8000. Please write down yourself. So 8000 is nothing but in this one. So first 00 starting from the LSP, the two bytes 00 are going to be called as a lower byte. So whereas the 80 is going to be called as a upper byte. Okay. So if I take the memory locations, let us take the memory location is going to be started with the 2000. 2000 is the memory location. So according to the little Indian, lower order byte of the data is stored in the memory at the lowest address. So let us take 2000, 2001, 2002, 2003, like that we are having a memory addresses. So the 00 will be stored in the 2000 and 80 is going to be stored at the 2001. So that's going to be called as a little Indian. So lowest address is going to be stored with the lower byte, and next higher address is going to be stored with the higher byte. Whereas in the so that's going to be called as a little Indian. Whereas if I go for the big Indian, so there in the big Indianness, the reverse will happen. So that is something bad. So here, in the previously we have seen that the the higher order byte of the data is stored in the lower address, and the lower order byte is going to be stored in the higher address. So that's going to be called as a big Indian. So previously 2000 is stored with the 00 and 80 is going to be stored with the 2001. So that's going to be called as a little Indian. Whereas If I go for the big Indianness, so little big Indianness, so the things will be differ. Starting with the, let us take the same 2000 and 2001, something like that. So the addresses are going to be having. Then, so first it will store with the 80, and second it is going to be stored with the 00. So that's how. So that's why. So in the I mean to say in the PPT I have given that one. So byte 0, byte 1, byte 2, byte 3. So first in the little Indian, so the first byte is going to be stored in the lower address. So that's the 2000. So in the second byte is going to be stored in the 2001. The third byte is going to be stored in the 2002. The fourth byte is going to be the 2003, like that. So that's going to be called as a little Indianness. So from the base address 02, so it's going to be stored like that. So whereas if I go for the big Indian, the reverse will be happen. So the byte 3 is going to be stored first, then it's going to be stored the byte 2, byte 1, and byte 0. So depending upon the addresses, different addresses. So like that. So that's how we're going to be having the little Indianness and big Indianness. So this is one of the important terminology which we need to know if I need to know about the embedded system. Next. So what we are going to be having is the next thing is going to be called as a load store operation. So what is the meaning of the load store architecture? So you can able to say as a load store operation or load store architecture. So like this, these are load store operations we are going to be having. Let us take, so the concept of load store architecture. So RISC processors are orthogonal, meaning that it can operate on any registers. So the memory axis, so we can able to, the memory axis related operations are performed by the special instructions, which is going to be called as a load and store. So let us take, I'm having a data in my memory. So the data is going to be stored in the memory. Okay. So I need to take the data into the microcontroller. So how it is going to be taking the data is called as a load store process or load store operation. So in the RISC, it's going to be having this load store procedure. So from the memory, it will take into the registers, and there it is going to be doing some operations. Again, it is going to be stored into the memory. So loading from the memory, and again it's going to be storing into the memory. So that's going to be called as a load store operation. For example, I have seen a diagram. I have given a diagram here. So where R1, R2, R3 are going to be called as registers, and ALU is nothing but arithmetic logic unit where the arithmetic operations are going to be performed. So I am having a X, Y, Z. So those are going to be called as the memories. Okay. So there in the X location we are having a 00, in Y location we are having a 7F. In the Z location, so we need to store that whatever the data we are doing. Let us take, they are having a instruction something like this: load R1, X. So what is the meaning of, they're given the dotted line. So load the X value into the R1. So this one. So these are load X value into the R1. Next, load R2, Y. Load the Y value, which is in the memory location, into the R2. Next, add R3, R1, R2. So add the R1, R2, and which is going to be loaded into the R3. So there's the indications we are going to be having, third operation and third operations. So after that one, store R3, Z. So this is going to, so whatever the results we are going to be getting in the R3, so this is going to be stored into the memory location. So that's going to be called as a load store architecture. So this load store architecture is only possible in an instruction set which is having an orthogonal. The orthogonal instruction set is available in the RISC computer. So the reduced instruction set computer only. So orthogonality means we can use any addressing system and we can use any register. So that's going to be called as the orthogonality. This orthogonality, can be utilized in the RISC. Okay, so there's a kind of RISC, and we can able to have the load store operations. How the load store operations are going to be performed. Next step. If I go for the next thing, which is a very important thing. So in the conventional instruction execution, let us take, I'm having a move AX comma BX. So this is called as a one of the instruction. Let us take an example, move AX comma BX. So what happens? So it's going to be executed with the following. First, the instruction is going to be fetched from the memory. The instructions are stored in the memory. We need to fetch that one instruction. Next, we need to decode the instruction. So decoding the instruction is nothing but, so move cannot be, MOV cannot be understood by the processor or controller. It needs to be decoded. So that can be done in the decoding process. Next, after that one, it needs to execute. So after that one, we need to execute such that the data between the BX register is moved to the AX register. That's the example. So we need to have the three things. One is going to be called as a fetching operation. Second one is going to be called as a decoding operation. Third one is going to be called as the execution operation. Fetching from the memory and decoding is nothing but giving the control signal, necessary control signal. Execution is nothing but perform the ALU operation, so arithmetic and logical operation, and it needs to store into the memory. So this is going to be called as a normal program execution. Whereas if I go for the pipelining, let us take, I'm having a continuous program, move X comma BX, move CX comma DX, something like that. So in the first clock pulses, or is the first mission cycle, is going to be fetching. So after that, the mission cycle 1, it started to execute it. Okay. So if I go for the mission cycle 2, so then what is going to be having is, so it, so in normal case, so in the clock mission cycle 1, it is going to be fetched. In the second mission cycle, it is going to be executed. Like that. So fetch, decode, and execute it. That is going to be, but if I go for the pipelining, so why? Because whenever it is going to be fetching the data, so in the normal CISC processor, so it's going to be having only one memory, one address, so shared address line. So that's why, so that the address lines are going to be, the buses are going to be very busy. So that's why it needs to wait. After fetching, it needs to wait for the decoding. After decoding, it needs to wait for the execution, like that. Whereas if for pipelining, first it's going to be fetching, and because we are going to be having a different buses, it's going to be having a fetching. So it doesn't wait for the next fetching. It continues for the next fetching. So in the next clock cycle, it continues for the next fetching in the next clock cycle. The execution will be started in the clock cycle itself, like that. So the fetching and executions are overlapped. So what happens is, because of this pipelining, the execution will fastly, it execute very fastly. So that's the use of the pipelining. So these pipelining are going to be utilized in the RISC processors. So nowadays, every processor is going to be having a RISC processor. So with this, so we are going to be completing the third day. So they are going to be having some lot of interruptions in the third day. So let's hope you have understood well. So next, so I don't want to extend this one. So next interruption. So next we will go for the one more block, which is going to be called as the memory. Memory is a very important thing. So these are different memories are available. So like we are going to be having a code memory, which is called as the ROM. So the ROMs are going to be having a different classification: flash, NVROM, PROM, mask ROM, EPROM, EEPROM. Like this, we are going to be having a different types of memories. For example, if I go for the masked ROM, MROM. which is called as a master RAM. So one type programmable, so this is a one type programmable device. So master RAM makes use of the hardware technology for storing the data. So like it's going to be a hardware is nothing but permanently it's going to be stored. That thing. So where it is going to be utilized is whenever the factory programming. So whenever the so let us take in normal terminology, in if I take the laptop, it's called as a BIOS programming. So basic input and output programming. So there, so this is going to be utilized like that. So in the washing machine programming, in the washing machine is the embedded system. There we are going to be having this type of master RAM. So it's going to be masked in the permanent program like that. So next, we are going to be having a PROM. So unlike the masked RAM, one-time programmable. So this is going to be called as a OTP, one-time programmable memory. So programmable read-only memory or PROM. It's going to be, so these are not pre-programmed by the manufacturer. The user can be programming this one. So here we are going to be having a nichrome or polysilicon wires arranged in a matrix. So we can able to burn this one. So those are going to be called as a fuses. So you may know this one. Fuses are going to be burned. So depending upon that one, there we can able to store ones and zeros. Our data is going to be stored. Next, EEPROM is going to be called as a erasable programmable read-only memory. So yes. So and we are going to be having EEPROM. So EEPROM is a electrically erasable programmable read-only memory. If you see the 8085 diagram, or there we are going to be having a one IC with the opening. So there's going to be called as the EC. Next, Flash. Nowadays the Flash programming, Flash are going to be utilized in most recent technology. So every embedded system they are going to be using now Flash. So the Flash memory is one of the variant of the EEPROM, electrical erasable PROM. So the difference between is we can able to program number multiple times rather than the EEPROM. So we can able to program multiple. So that's going to be called as a flash memory. Next, we are going to be having a non-volatile NVROM. So random access memory, which is going to be having a battery with the backup. So right like that we are going to be having. Next, if you see the RAM, so the RAM is going to be having a read-write memory. So we are different classification. We are going to be having a static RAM and dynamic RAM and NVRAM. So if I see the static RAM, so we may know this one, very simple one. So here it's going to be having a 6 transistors or 6 MOSFETs. So it became as a 1 bit. It can be stored 1 bit. So say by using 6 transistors, it can be used. So we will have static RAM. So so this is one of the fastest form of the RAM. So available RAM. So this is going to be one of the fastest RAM. So you can able to see this one. So this is the construction we are going to be having. So next we are going to be having a dynamic RAM. So dynamic RAM is going to be having something like this. So what I will do is I will give the differences. So SRAM is going to be having up to 6 MOSFETs. So whereas here in the dynamic RAM, along with the MOSFET, we need to have a capacitor. So we're going to be utilizing a refreshing. Next, it doesn't require any SRAM doesn't require any refreshing circuitry, whereas the DRAM requires a refreshing circuitry. Next, SRAM is going to be having a less density. Less density is nothing but we are having a low capacity. So DRAM is going to be having a highly dense, that's nothing but a high capacity. So that's why DRAM is going to be. Next, SRAM is a more expansive. So whereas the DRAM is going to be having a less expansive. Next, fast in operation, typically access time is at 10 nanoseconds. So the static RAM is a very fast. So that's why static RAM is a very fast, and the dynamic RAM is slow in operation. It requires a refreshing circuitry also. This is another thing we are going to be having. So with this we are going to be completing the day 3. So I hope in the next class I will try to connect my touchpad so that we can able to give the examples directly. Okay. So in the next class, we will try to discuss about the architecture of the 8051 microcontroller. Thank you for thinking. So if you are having any doubt, please ask me. Anybody having any doubt? If you don't have any doubt,